Hello students, I hope that you are good, well and fine. And today we will be continuing our discussion on the topic of relations and functions. In this, we will be mainly focusing on functions. So let's see what we are going to discuss. So we will be covering composition of function and then invertible function and then equality of function. If time permits, we will do the questions based on these concepts. Okay. So without wasting our time, just see our first subtopic, which is composition of functions. So now let f from a to b. So my domain is a for f function f. Domain is a and codomain is b. And there is another function g defined from b to c. Now b is my domain and C is my codomain over here. Okay. B2 functions, then the composition of F and G denoted by this is my composition GOF, F and G defined as the function of GOF, okay, from A to C. If you try to observe something, which is F is going from where to where? A to B, and G is going from B to C. As you can see that if F is there at the right side, okay, then first F operates on A and then leave it to B. And now if you try to see over here that G starts from B, where the F ends at B, okay, and then leave it to C. So as you can see that we started from A and ended with C. So that's why we write over here that G of F, this composition function, will start from A and end with C. Okay, if suppose that okay, so that's it. Okay. I hope that it is clear why it starts from A and ends with C. Okay. Now the G of Fx, what do we mean by that? This means that this function, my GOF, okay, the input is from X, input, or the domain, input or the domain is my what? Domain is A, this set is my domain, and codomain is C. Okay. So what this means? This means that first of all we will apply, or the F operates on X first, and then whatever the Fx gives me the output, okay, then the G operates on it. Okay, you will see with examples. Okay. So I hope that it is clear. So the one main thing to be pointed out over here is this: the codomain for this function F is same as the domain for this function G. Without this, we cannot write that my function goes to A to C, because the link between F function and G function is this. Yes, the F function goes A to B, then we know that G goes to B to C. If suppose that here we wrote D, then F goes to A to B and G independently goes D to C. There is no bridge. Yes. So B provides the bridge over here. So that's why when you whenever you do composition of function, always keep this point in mind, that this function codomain must be equals to domain of this function. Okay, without this you cannot define the composition of function. Now let's see an example. Suppose my fx is what? Say x from f is my from R to R, and gx is what? Say 2x, gx is also from say R to R. Okay, the condition satisfied. Okay, this codomain is equals to this domain. Okay, so this means g of fx will equals to be g of fx. And you know what is fx? We know fx is what? Sorry, fx is equals to x. So I can write just x over here. And now gx is what? Gx is 2x. So my g of fx will equals to be 2x. Okay. What about if I say, can you find f of gx? Let's try. First of all, let's see, can we do it or not? In order to do composition of two function, this function codomain must be equals to the domain for this function. Okay, domain of f and codomain of g. Okay, this happens every time. As you saw in this also, that this function codomain of f is equals to what? Is equals to the domain of g. Yes. Okay, so let's see the domain of g. Domain of g is what? Codomain of g is r. Codomain of g is r. Okay. What about the domain of f? Domain of f is also r. So yes, indeed we can define this thing easily. Okay, let's now evaluate it. So now this means f of gx. Okay, gx is what? Gx is 2x. Okay, so f of 2x. Now what we know, fx is equals to x. This means whatever the input we gave, the output will be the same. So this means here if you see that my input is 2x, this means I can so my output will be what? 2x, same as the input. As you can see, fx gives me the output as 2x. In here, whenever we give input as x, what we will get? We will be getting 2 times of x. As you saw over here, gx, the input is x, the output is what? 2x. And here input is 2x. In f give me the just same as the output as its input. Okay, I hope that it is clear from this example. Let me take another example so that you can get what we are doing actually. Okay, so f, let's define f as x square. Okay, and g as what? We can define g as fx is equals to x square and g as say just x. Okay, and f is from where to where? R to say just what? R to r. Okay, and g is from where to where? G is from say also r to r. Okay, now g, can we define g of fx? Let's see. The codomain for this is r. Okay, codomain for this is r, and domain for this g is what? As you can see, is r. So can we define it? Yes, as we can see, the domain and codomain of these function must be equal to each other. But if you see that okay, so this means we can indeed define this. Okay, but we know what we know, that every element in this set has image. Okay, so for this, yes, indeed. Okay, that's it. For the minimum condition is satisfied. Now what we will do is quite easy. So g of fx, we know what we know. We know that fx is what? X square. So g of x square. Okay. Fx is x square. So fx is x square. Now what will be g of x square? We know gx will be equals to x. So whatever the input we gave to g, the output will be the same as the input. So the output will be the same as my input. So the output will be x square. Okay. So this is my g of fx. Now what about f of g x? So the codomain for this is equals to the domain for this, as you can see. So if you define, so the output will be, or if you evaluate this, what you will get? You will get like this. Then the gx is equals to just x. So f of x. Now what f of x is equals to? Fx, what it will do? It will square the input. So whatever you give as x, it will do the square of it. So this means your output will be the same as the g of fx. Okay. So I hope that it is clear. And the conditions for to be composed to any composition of to any functions is what? The codomain of this function must be equals to the domain of this function. This means codomain of this must be equals to the domain for this function. Okay, I hope that now it is clear to you. Let's move to next. Let's see over here what is happening. So f is defined from this set to this, and g is defined from this set to this. As you can see, in order to find g of f, what we need, the condition is codomain for this, which is this, must be equals to the domain for this. As you can see, the domain is this. Yes, you can easily see that. 3459, 3459. Okay, we can indeed define and we can evaluate it. Let's find out. Okay, so here the f of 2, or just see visually by arrow diagram. Okay, so this is my set A, this is my set A, this is my set B, this is my set B, this is my set C. So set A is 2, 3, 4, 5. Set B is what? 3, 4, 5, 9. Okay, and set C, if you can observe, is 7, 11 and 15. Okay, now what? Now if we apply f, the function f applied A to B, okay, the image of 2 or the output for 2 under f is what? 3. 2 is related to 3. 3 is related to 4. 4 is related to 5, and 5 is also related to 5. Okay, 4 is related to 5 and 5 is also related to 5. Okay, now what? Now let's see about the function g. So g is from B to C. This means this will be my function g, and in g 3 is related to 7 as well as 4 is related to 7. This means 3 and 4 have the same image. 5 and 9 is related to 11. 5 and 9 is related to 11. Okay, now from this diagram, what you can give? If you find g of f x, okay, so what will be my input? The g of f, first of all, g of f will be from where to where? G of f will be, if you know that this is from A to B and this is from B to C, so my g of f will be from A to C. So I can write A to C. Okay, is this clear? Okay, quite easy. So now what? Now, so take, so g of 2. So this means g of 2, not g of 2, sorry, g of f of 2. What will be g of f of 2? G of f of 3, g of f of 4 and g of f of 5. That's the element of the set A, 2, 3, 4, 5. Okay, so g of f of 2, what it will be? G of f of 2, and f of 2 is what? f of 2 is 3. As you can see from this arrow diagram, 2 is related to 3 under f. So it is equals to g of 3. And now what is g of 3? G of 3, as you can see, g of 3 is related to 7. So it will be equals to 7. Now g of f of 3, g of f3, f3 is what? f3 gives me 4. As you can see over here, f3 gives me 4. f3 gives me 4. So g of 4, and g of 4 is related to 7. As you can see, g of 4 is related to 7. g of 4 is related to 7. Now g of 4, g of f of 4, f of 4 is what? As you can see, f of 4 is 5, g of 5, and g of 5 is what? 11. It is 11. And g of f of 5, f of 5 goes to 5, and g of 5 is what? Okay, g of 5 is what? Okay, g of 5. Okay, so g of 5 goes to what? 11. So g of 5 goes to what? 11. Okay, I hope that it is clear. So if you draw this A to C arrow diagram, A to C, and this function is what? G of f. Now 2, 3, 4, 5, and over here you can see 7, 11. The output is the C set is what? 7, 11, and 15. Now if you try to see, 2 is related to what element? 7. 2 is related to 7. 3 is also related to 7. 4 is related to 11, and 4 and 5 is related to where? 11. Okay. Now compare this whole diagram to this simple diagram. You can see that 2, as you can see over here, so here, so let me use this pen. So 2 is first of all related to 3, and then 3 is related to 7. So we can directly say from this pictorial representation that in g of f, 2 is related to 7. As you can see over here, 2 is related to 7. 3 is related to 4, and then 4 is related to 7. As you can see, 3 is related to 4. Yes, 3 is related to 4, and 4 is related to 7. So in total 3 is related to 7. As you can see over here, that's what it is happening. So 4 and 5 both related to 5, and 5 goes to 11. So this means 4 and 5 in total related to 11. As you can see from this evaluating part, we got the same result. So either you evaluate every element, or do just by this pictorial representation. So whatever you think is easy, please do that, and you will get the same answer from this method also, or from this method. Okay, I hope that you got the idea. Let's move to next. Now we need to find out the g of f and f of g. If my function is from R to R, and g is also from R to R, it satisfies the basic needs to composite any two functions, because in g of f what we need, the codomain in this of this function, codomain, let me write properly, necessary conditions for g of f. Okay, so for g of f is the codomain of f must be equals to the domain of g. As you can see, the codomain of f is R, and the domain of g is also R. So it is satisfied. In if you see in this composition f of g, what we need, the codomain of G must be equals to the domain of F. Domain of F. So that's the first thing we need to find out the composition of any two functions. So it satisfies both. Okay. Now let's find out fog and gof. In short, we say gof, and in short we say fog. Okay. So now let's see, as fx defines fx is equals to cos x. So fx is equals to cos x and gx is equals to 3x square. Gx is equals to 3x square. Okay. Now what we need? So first of all, let's find. So f of gx is equals to what? F of gx, and gx is what? Gx is my 3x square. Now fx, as you can see over here, that fx, when f is operating on x, what will be the output? Cos x. Yes. Okay. So whatever the input given as x, the output will always be the cos of input. Okay. So the output will be cos of input. Cos of input. Okay. As you can see, cos input. Here input is what? X. This is my input. This is my input. So output is what? Cos of input. So here input is what? Here input is this input. So this means my output will be cos of input. Cos of input means cos 3x square. Okay. Now what about gof? So in gof, what we need is g of fx. Here fx is what? Cos x. Fx is just cos x. Now what g do? So whatever the input, what it will do? It will 3 times input square. This will be my output. So I will write what? I will write 3 times the input. Input square. Input is this. So input is this. Input. Okay. So input is cos x. So cos x whole square. As you can see, 3 cos square x. So this is my what? Gof, and this is my fog. As you can see, both are different functions. Okay. And as you can see, what we need to show, that g of f is not equal to f of g. Okay. So this means this relation, or this relation given to us, both are different from each other. When do we say that two relations are different from each other? We say whenever we got a pair, such that AB from this relation, and there is, let's say there is another say, okay, so let's say just pick there exists some pair AB in this, which is not belongs to this set, not belongs to the set of this, or vice versa you can say. Okay. Or there is another way to see what, that cos 3x square is equals to 3 cos x whole square. Can you think any x such that this happens? This cannot happen. Can you think any x such that this cannot happen? Yes. So if you put x is equals to 0, what you will get? This as 1, and this what you will get? So 3 cos 0 will be what? 1. So this will be 3 times 1. You know that this is not equals to 3. So this means the fog and gof are not equals to each other. Okay. You will see when we say, you will be seeing later on that when we say that two functions are equal to each other, two functions are equals to each other, or not. For now, just keep this point in mind that whenever you can find, if you have some x such that fx is not equals to gx. Okay, some x, say some x naught such that fx naught is equals, does not equals to what, the gx naught. Okay, or say just gx for every x, okay, belongs to the domain of G. I know that it is not the correct definition, but for the time being, let's suppose that if you find such x naught, okay, which is not equals to what, the gx for every x, we say that two functions are not equals to each other. Okay, and I hope that it is clear to you. As we saw that we found out that both of the elements are not equals to each other. Okay, let's move to next. Okay, let's move next. So here now we will see the invertible function. Okay, invertible function, what do we mean by that? A function f from x to y is defined to be invertible if there exists a function g, okay, there exists a function g y to x. Okay, keep this point in mind. If fx is defined from x to y, keep this point in mind that if f is invertible, then the function g, the other function g, is defined from x to y, y to x, as you can see over here, y to x, such that the composition of g of f is equals to ix and f of g is equals to iy. So what do we mean by that? You will be seeing what do we mean by that. This is what the identity function in terms of x, and this is the identity function in terms of y. Okay, then if this exists, such that this happens, then the function g is called the inverse of f, and it is denoted by this. Okay, so I hope that the definition is clear to you. So thus, if f is invertible, then f must be, so this means f must be 1 1 and onto. Okay, and conversely, if f is 1 1 and onto, then f must be invertible. So the necessary condition, or the very important condition to be that there exists an inverse is, first, f must be 1 1 as well as onto. Okay, so this must happens, then only the f there exists f inverse. If f inverse exists, this means f must be 1 1 and onto. If f is onto, then there exists inverse. If f inverse exists, then this means that f must be 1 1 as well as onto. Okay, so both way we have 1 1 and onto ness of f. Okay, let's move next. From an example, we see f defined from a natural number set to what, y set. Okay, it is defined like this: fx is equals to 4x plus 3, where y is set such that collection of all natural number such that y is equals to what, 4x plus 3, for some x belongs to the natural number, so that f is invertible. So in order to show that f is invertible, we need to show that f is 1 1 and onto. Okay, let's show that. So for 1 1, what we in order to prove 1 1, what we start okay, so we always start with this fx1 is equals to fx2, and what from this we need to show that x1 is equals to x2. If we will succeed, okay, to prove this, then we will be saying that this f function defined over here is 1 1. Okay, let's start. So if fx1 is equals to fx2, this means 4 of x1 plus 3 is equals to 4 of x2 plus 3. So just do some manipulation, you will get this, and from this you can write that x1 is equals to x2 for every x belongs to the natural number set. So this means whenever this happens, we will be having x1 is equals to x2. So it is indeed 1 1. Now let us prove for onto. In order to show onto, what we will start with, we will be starting with taking fx is equals to y, then putting a y in place of x. What you will get? 4x plus 3. Yes, so 4x plus 3, and then what we will try next, we will be trying that try to write x is equals to some expression in y. Let's do it. So doing some just rearrangement, okay, so what you will get is y minus 3 by 4 is equals to x. So this is my equation of this type, x is equals to some expression in y. Okay, I hope that it is clear to you. Now what we will do, we will be trying to see that what value of y we can put over here, and what restriction y is having, and also what value of y we will be putting such that x over here must belongs to the, we know, because we know this is equals to x and x must be belongings to the natural number set, and this cannot be disobeyed. Okay, as you can see, y taking all such y, so we will be taking all y, so we will be taking all y such that what happens, 4 minus 3y belongs to the natural numbers. This means y minus 3 by 4 is equals to x must belongs to the natural number. Yes, this means y minus 3 is equals to 4x belongs to the natural number. This means 4x plus 3 belongs to the natural number. So this means all set of all y such that this happens. As you can see, the codomain is y, and y is the all such elements from the natural number such that this happens. Okay, so this means, what this means, we showed that what we showed is the values of y, set of values of y is equals to the codomain. This means range is equals to codomain. This means it is onto. So we showed that it is 1 1 and onto. This means there exists f inverse. Now we have to find the inverse of this function. So how do we find it? It is quite easy. What? So here whatever we got is my f inverse. So but how I am going to write it? So whatever you got in this such type of expression will be your f inverse. So we got x is equals to y minus 3 by 4. This means just replace, okay, just replace x to y and y to x. What you will get? I will be replacing like this. Okay, like this. Now just put y is equals to gx because it is inverse. So just say this y is equals to f of inverse because it is inverse x minus 3 by y, 3 by 4. And now do composition. If you do composition, say f inverse of f, what you will get, as you know, f inverse of fx, and fx is what? Fx is 4x plus 3. Now as you can see from here that f inverse input will be f inverse input will be what? Input minus 3 by 4. Yes, so here this is my input. So it will be what? F inverse input is input minus 3 by 4. Okay, so input is input minus 3 by 4. So this means this will get cancelled. So 4x by 4 will be your what? So as you can see, f inverse of f is what? Identity in x, as you can see over here. If you try to find the f of f inverse, you will get what? Let's see over here. So you will be getting x. Let's see. So f of f inverse is what? F inverse is f inverse x, and we know f inverse x is what? F inverse x is x minus 3 by 4, and fx will be what? 4 times x minus 3 by 4 plus 3. So this, it will be what? X minus 3 plus 3, you will get x. Okay, I hope that it is clear. So in both cases you will get, if there exists f inverse, then you will get what? So keep this point, remember, note, if f inverse exists, then whenever you try to find out this, you will get x, and whenever try to find out this, you will get x. Okay, I hope that now it is clear to you from these examples. So that's it for today from my side. We will meet next time with more questions. So thank you.